Welcome to this video lesson. In this video, we will be looking at the basics of force of friction. Let's start off this lesson with this little activity. So we're going to draw a free body diagram of a binder or a tablet or a notebook on a table. So imagine that you have a table and on top of it you have some sort of object. It could be anything. It could be a textbook. It could be a binder. Or tablet, it doesn't really matter. We're going to call this an object, and we are going to draw a force diagram on it. So to do that, we are going to isolate it and make it our system, and our system here is our object, and the forces that are acting on it, there's going to be a force of gravity, or the gravitational force acting on our object, and then there is going to be a normal force acting from the surface here. I'll just call this surface on our object, and that's it. Those are the only two forces. We can see that these two forces need to be balanced. So use the second law to determine what is the reaction force equal to. The reaction force we're referring to here is the normal force. Sometimes we call it reaction force for short. And that's from the surface onto our object. So I'll just use Fn here. And second law of motion, I am going to say F net y is equal to the summation of the forces, and we have two forces acting here, so it's Fn SO plus Fg acting on O, and all of that is going to equal to mass times acceleration. In this case, we know that the object is stationary, so it's not moving, so it doesn't matter which way we take positive to be. I'm going to take it up to be positive. In this case, I have up and up, so this force is positive. When I turn it into magnitude, and the other force is negative because it's acting downwards, and that's going to equal to mass times acceleration, and acceleration, let's assume it's going upwards. It doesn't really matter because its value is 0. This is going to equal to 0 because mass times a value of 0 is going to be 0. And if I rearrange this, I will get that the normal force, its magnitude, is equal to the gravitational force acting on my object, or mass of my object multiplied by the gravitational, or the magnitude of gravitational acceleration. So this is kind of what my force is. Now, we're going to start by pushing the object horizontal to the surface. Start with a negligible force and slightly increase the force. With a small force, the object will not move. The frictional force is resisting the force that you're putting in. Is this frictional force static or kinetic? Well, in this case, static refers to things that are stationary, and kinetic refers to things that are in motion or moving. So in this particular case, if you were to put a small force on a binder, just like a tiny touch, there's a little bit of force that you're putting in just even by a touch. And that's not going to move the object because there's a force of friction kind of stopping the movement. And this force of friction is going to be a static case. And this is because no movement is happening. As you push harder, there will be a point at which the object will start to move. How does the size of force of friction before the object moves compares to after its movement. So if you have an object, I have a stapler on my desk, which is heavy enough so it's kind of easy to experience this. But if you were to just if you started touching the object, imagine it's your binder or your tablet, whatever device you're using, or even your monitor, as you touch it, it's not going to move. You're going to push it, push it, push it, push it more and more and more, and at some point, it kind of slips. And as soon as it slips, the force that requires to move it, it decreases just slightly. It's always different for different cases. For some objects, you will notice it a lot more than others. And we'll talk about coefficient of friction a little bit later. But often what happens is you reach, I'm just going to write here, reach a max force, and when it starts to move, the force drops slightly. And I'm saying slightly, it's not always slightly, sometimes it's a little bit more, sometimes it's a little bit less, but it changes a little bit, and you will experience that if you try it in many different objects. You will definitely feel it. Now, what we're going to do is now for the next little section, ask your partner to push the object down. Let's call this force a force from person on an object. You don't need a partner to do this. If you're at home, you can just use one of your hands to push the object down onto the table and draw the new force diagram on this. So we are going to have our object, it's on a table, and we have somebody who is pushing it downwards. Let's call this force from person onto the object. And now we are going to isolate our object again. My system is going to be the object and the forces acting on it. There's a gravitational force. There's now an applied force. Let's say we're pushing at a pretty significant force, and that applied force is from the person onto my object. That's this force over here. And so I've taken care of the top surface, nothing in contact to the side, but in this side there's also a normal force acting upwards, and the object is still stationary. Even as you're pushing it, it's not accelerating up or down. So I am going to draw this force the same size as the addition of these two forces, are approximately the same there. I'm going to try my best. And this is going to be normal force acting, or the reaction force acting from the surface onto my object. And if I were to use the second law of motion to find this new reaction force, I am going to write that the net force in the y direction, taking up to be positive, or doesn't really matter for the first part, is going to equal to the sum of all forces. So we have FNSO plus FG plus FPO, and that's going to equal to the mass of my object multiplied by its acceleration in the y direction. And I'm going to turn all of these into magnitudes. I got positive and positive, so this is going to be FNSO. This force is acting downwards. This is up, so I'm going to use a negative. Now I'm only dealing with the magnitudes. I'm just going to label this as O. And this force is also acting downwards. This is going up, so it's going to be negative force from person onto the object, and that's going to be the mass. And the acceleration, I'm going to assume it's going upwards as well. It doesn't matter because it's going to be 0 in a second. For this line, 0, because if the acceleration is 0, 0 times any number is 0. I'm going to add these two to both sides, and I'm going to get that my reaction force from the surface acting on my object is going to equal to the gravitational force acting on my object plus the force from the person onto the object. You can also write this as mass of the object times the magnitude of gravitational acceleration plus the force from the person onto the object. So these are two different ways of writing it, but you can see that in comparison to before this force was added, the normal force acting was only the gravitational. Now it's the gravitational force plus whatever force is being added on in there. Now try pushing the object again. What do you notice, and why did this happen? Now, whatever object you had, if you try pushing it now, it's going to be a lot harder. So let's say this is without anybody pushing it down, but if you try pushing this, if somebody is sitting on it, or you got a group of friends just sitting on it, it becomes a lot harder to push. And this extra force that's acting on it downwards increases that reaction force. And that reaction force, or the normal force, when it increases, it becomes more challenging to move the object. So this is an interesting investigation. It lets us know that as normal force from the surface onto the object increases, the force of friction also increases. This is really, really, really interesting. And it's something that we can observe, so this is actually pretty nice. Let's try to understand what's happening here. And to do this, we have to zoom into the contact between the two surfaces. If we zoom enough, we will see imperfections in our two surfaces. And both surfaces will have these, and in different magnitudes, depending on the surface, depending on material and other things, these imperfections exist. And initially, if you were to try to move these two, they would try to slide over each other. And microscopically, you can see that some of these peaks are in contact with these peaks in terms of surfaces, and as you try to move these, they will interact, and that interaction is what's causing that force of friction. Partly it's that, so it's the type of surface, but it's also the material as well. So some materials, when they are in contact, they have a much bigger ability um, to cause force of friction. So some of the stuff that is important, one is material, another one is smoothness of the surface. It's also important because if the surface is much smoother and this one is also much smoother, it will have an impact on the force of friction. Now, just assuming that the smoothness is the same material becomes very important. But as we try to move this, we can see that in this case there's some spacing between these, and that helps to move the object. So when you try to move it, some of these are interlocked, but as soon as you start moving them, they will start sliding over each other, and that's why in the beginning it requires a little bit more force, but once it starts to move into the kinetic region, or once it starts to move, it becomes a little bit easier, because then it's like the objects are just sliding on top of each other and they're no longer as interlocked. But what happens when you look at the contact between the two forces when there's extra force acting on it and when the reaction force is higher. If you have the imperfections on top, uh, when you put that extra force, the objects are much closer to each other. And these interlocks there's just a lot more interlocks between the two surfaces. And because of this, as you try to move it, there, like all these sections that are in contact with each other makes it much harder for you to move it. So when there is no force, there's a little bit of a gap between these that allows you to move it. But as soon as you put force on it, microscopically, these little interlocks are filled in and there's no longer that much gap. So as you're trying to push it, if you have two surfaces which are really um, two surfaces which kind of look like this versus two surfaces which look like this, it's a lot easier to move this because of this small gap. It just slides over it, whereas this one, it's going to be harder, especially if there's a lot of these imperfections and they're all so close to each other. So that's why this is happening. As you put more force, as the normal force increases, the gaps reduces, and that increases the force of friction. All right, so using a solid line, sketch the new position of force of friction. So before doing this, let's talk about what this graph actually means. And before actually doing this example, we're going to go back and um, I think now we have covered enough to talk about force of friction in a little bit more detail and give you some idea about some of the definitions that you need to know. Friction is a contact force that occurs when two objects that are pressed together try to slide against one another. So that mainly becomes microscopically, they have imperfections, they interlock, and as you try to move them against each other, there's going to be the force caused by those interactions. If the surfaces are sliding relative to one another, we call the force kinetic friction. If the two surfaces are not slipping, we call the force static friction. So static when the objects are not moving, whereas kinetic friction is when the two surfaces are sliding on top of each other. The size of force of static friction can take a range of values depending on what is happening in the particular situation. There is a few things you need to know. So force of friction is usually written like this. This for force, this for friction. I like to use a curve. Not everybody does this, but it helps distinguish friction versus other letters. And you have force of friction. This stands for static. And if you notice, if you were to touch an object, you will start right away having some force of friction, especially if you're putting a force in a direction that might cause the object to slide over the surface. And as you keep pushing it, this force starts to increase. So let's say we got this buddy, a heavy box here, trying to push the box. And initially, this person puts a little bit of force in there. So let's say this much, and it's somewhere here. So the applied force by this person, this little force is this much. And the force of friction is exactly the same amount as pushing it backwards. This should be a little bit more on an angle like this. And then the person decides to push it a little bit more. And then they're somewhere here. They're still pushing hard, but the force of friction from the surfaces is pushing it back the exact same amount. And then this person pushes it much more, and they reach what's called the max static force. This is the force just before the object starts to move. and that's right here. We call that the max static force. And once it starts to move, the force of friction, which is this one, starts to reduce a little bit. And this is what I was talking about when I said when you have the two surfaces, I'll draw them using different colors, and um, they're kind of interlocked so nicely here. Once it starts moving, the object will the it starts moving like this, and the gap starts to reduce between the two, and the object can starts the objects start to slip over one another without going through all the gaps all the time. If there was a reaction force, it would make it a lot harder, but when the gaps are present, it's a lot easier to move. And that's why once it starts moving, the force of friction is reduced by a little bit. And in reality, that force, a lot of times we model it as a straight line, but it actually fluctuates because as you're going through these bumps, sometimes the surface hits certain bumps and the force goes up slightly, and then sometimes you have gap spaces, so it goes down, and it's not by that much, so it's insignificant, so we can draw this as a straight line. But in reality, there's a little bit of a fluctuation here. This force is what we call force of kinetic friction. So it's pretty constant throughout, whereas static friction is not really constant, it changes. You keep pushing, it keeps pushing you back until it starts to move. And once it starts to move, that force of friction becomes approximately a constant value. So just continuing this line, there's a maximum possible value for the force of static friction, which occurs just before the object begins to slip. This maximum value is usually greater than the force of kinetic friction, and that's this one over here. The coefficient of kinetic friction is shown by this letter, mu. So mu is like a U with a little line here. It makes it a mu. It's pronounced like the sound that a cat makes. And if I write it like this is called the kinetic coefficient of friction. And the static one is mu s. This is static coefficient of friction. This depends on physical properties such as the roughness of the shape or the smoothness of the surfaces, and the chemical compositions as well of the pair of the surfaces. So not just one surface, it's dependent on both. Related by expression, and it's related to force of friction by this expression. Force of friction is equal to this coefficient of friction, coefficient of friction. I'm just going to write it as just mu actually, because if it's kinetic, it's mu k, and if it's static, it's mu s, multiplied by the reaction force, or the normal force. We saw that the normal force has an effect on force of friction. As normal force increases, force of friction increases. But now we can see that the coefficient of friction also matters. So if the surfaces are super smooth, for example, this value decreases and the force of friction decreases. If the surfaces are very rough, this increases and force of friction also increases. So force of friction is dependent on two main concepts, and this coefficient of friction is mostly dependent on which two materials are in contact. And we'll give you some examples of some of them at a later time. And we can find So basically we can use this equation all the time. The force of friction kinetic will equal to the kinetic coefficient of friction multiplied by the normal force, and the maximum static force of friction can be calculated by the static coefficient of friction multiplied by the normal force. This is our new best friend. All right, let's go back to our last part of the investigation here. We say use a solid line to sketch the new position of the force of friction, assuming that the dashed line present a situation in which you or your partner is not pushing on the object. So this is the case where this is the static region where if you're putting a force, the force of friction is the same. Force of friction is the same. This is before the object is moving. And once it starts moving, as you put more force on it, the force of friction stays constant. If you are putting if you're changing this and if you put more force, more force on top of it, if you push it down, then as you keep pushing it, it's going to become, it's going to be the same, it's going to be challenging to push it, but that static force of friction is going to increase, and then after some maximum force, it's going to decrease, and you are going to have a force of kinetic friction like this. So basically, if someone's pushing on it, the maximum force that you require to move the object is going to be much more because there's just so much more interlocking um, that's happening between the two surfaces. All right, let us now use the idea of force of friction to solve some questions, and we're going to start simple. In this question, we're going to use the 5-step technique. So I'm actually going to leave a little bit more space here. The kinetic and static coefficient of friction between two surfaces are 0.3 and 0.4 respectively. If an object of mass 5 kg is resting on this surface, what is the minimum force required to move it to the right? Okay, let's draw this situation. In this situation, we will have an object and we are trying to push it. The static coefficient is 0.4. The kinetic is 0.3. These are always, the static will always be higher in most cases. Because it's usually much harder to move the object statically. Once it starts moving, it becomes easier, and therefore the kinetic force of coefficient of friction is going to be less. What else do we know about this question? So that's kind of all we know. We know that the person is going to be pushing it. We don't need to draw movements in here. There's no stage 1 and stage 2. This is everything that's happening between the stages. Just trying to get it to push. So we don't have to draw the motion diagrams. But in terms of a force diagram, we have our object and we are going to put a force on it. This is the applied force, let's say from the person onto the object. And there is going to be a gravitational force acting on it. So I'm going to write that as Fg. There is going to be a normal force acting from the surface onto the object. I'm just going to use normal force here. I'm not going to write from surface onto the object just to make it a little bit easier. And there is going to be force of friction acting on it. So I'm going to write that here. Okay, in order to find the force of friction, we always need the normal force. And sometimes we can find it using other ideas, especially if we have the acceleration, but if we don't have that, we do need the normal force. And to find a normal force, we can use the we can use the second law of motion in the vertical direction. So that's what we're going to do. Just forgot to include one piece of information here, which says mass is 5 kilograms. Okay, in order to find the normal force, I am going to write the net force in the y direction. And this is going to be the sum of the forces acting in that direction, which is Fn plus Fg. And I'll take up to be positive, and I'm going to say this is equal to mass times acceleration. The force here is moving upwards, that's positive, so I'm going to use Fn. When I turn it into magnitudes, this one is going down, this one is going up, opposite minus. This is going to equal to mass times acceleration. Acceleration in the upward direction, as I'm pushing it, it's not accelerating up or down, and this is going to equal to 0. Rearrange, and I get Fn is equal to Fg, or Fn is equal to mass times gravitational acceleration. In your questions, if there is no force acting down or up on your object, then these two forces always need to balance. If that's the case, then you don't have to write this. You can right away say that the normal force is equal to the gravitational force. Writing this is helpful, especially in the future when you're dealing with two-dimensional forces, and also in situations when there are other forces acting vertically on our object. In that case, you always have to write this. But if the only forces acting are the gravitational and normal force, then you can right away say that the normal force its magnitude is same as the gravitational force's magnitude. Okay, now I have the expression for my normal force. I will now need to find, in terms of assumptions, basically, if there's any acceleration, it's going to be constant. If there's no air resistance, so there's no other extra forces pushing it back. And those are the two main ones here. Okay, and what was the first question? Part A, what is the minimum force required to move it to the right? So the minimum force, so initially when the person is pushing it, it's not going to move. To move, we need that minimum force, which is equal to the static force of friction. And that is equal to the static coefficient of friction multiplied by the normal force. In this case, I actually just need the magnitude of the force, so I don't need it in terms of direction, so I'm just going to erase this. And this is going to equal to mu s, which is 0.4, given to me in the question, and Fn, which I just found out as mass times gravitational acceleration. 0.4, my mass is 5, my gravitational acceleration is 9.81. And when I do all of this, I get 19.62 newtons, which is approximately 19.6 Newton to 3 significant figures. And this is the minimum force required to start moving the box, or the maximum static force there. In this case, they're the same value. For part B, it says if the object is moving to the right at a constant velocity, what is the force of friction acting on it? If it's moving to the right at a constant velocity, it means that it's not accelerating. So I am going to write a net. So we're trying to figure out what this force over here is. So what force is acting on it if it's moving at a constant velocity. So I am going to, we can do it in two different ways. I'll do it the long ways just to make sure that you understand how to write net force equations really well, because I want you folks to master it. So the F net in the x direction is going to equal to the sum of forces in the x direction. In the x direction, my two forces are these two. So I have the force acting from person onto the object plus the force of friction. And that's going to equal to the mass of my object multiplied by the acceleration in the x direction. I'm going to turn everything into magnitudes. So I have magnitude of this force, the magnitude of this force, positive, so I'm going to use a positive value. Here I have this force going this way, opposite to my positive, so minus force of friction. And sorry, before moving on, this force of friction now, in this case, because my object is moving at a constant velocity, is going to be the kinetic force of friction. Whereas in the last one, it was just before it was moving, it was static, and now that it's moving, it's the kinetic. And this is going to equal to mass times acceleration. And my acceleration doesn't really matter. My acceleration here is 0, so this whole term is going to equal to 0. And the force of person on object is going to equal to the force of kinetic friction. Force of kinetic friction can be calculated by the normal force multiplied by the kinetic coefficient of friction. The normal force I've calculated here already. That's m times g. I'll just plug in the numbers. Actually, no, I'll write it out. mg times mu k. Mass is 5. G is 9.81. Mu k is 0.3. This is 14,715. And in 3 significant figures, that's 14.7 newtons. And I'll just write this down. This is because it's constant velocity. And this is max force before it moves. And that would mean that you have to put at least this much force before the object can start to move. And that's why we say it's the minimum required force in order to push it. And once it starts moving at a constant velocity, you need a little bit less force to put in. You only put 14.7 Newton in there. And that's it. That's how you would solve this question. In terms of evaluation, this would make sense because the force that you require to move the object when it's moving, it's less than the force or the maximum force before moving it, so this checks out. We can add some ideas in here, so we can say what happens if there's air resistance, and if there's air resistance, there's going to be particles colliding here, so this force is going to increase, and you will need to put extra force in order to move it. It doesn't change the force of friction because force of friction is only dependent on the two surfaces and the normal force. We can ask you what happens if we were to put an extra force in there, and that would mean that the force of gravity is going to, the force in this direction is going to increase, and in order to balance it, the normal force is going to increase, and therefore force of friction will increase, and therefore this force will also increase. So there's so many different ways of evaluating this, but in terms of whether or not it makes sense, it does. And the other thing in terms of coefficient of frictions, they're always dependent on surfaces. So sometimes we would give you a chart with two different type of surface, let's say steel to steel or steel to ice or other objects, and we just tell you what surfaces they are, and you would look at the chart and you will figure out what these values are. We find these values purely based on experiments, so we will actually experiment and figure out what is the coefficient of friction between plastic and plastic, or plastic and wood, or different types of plastic and different types of woods, and we just make charts for it. That's what engineers do. We do research and we figure out what these coefficient of frictions are so that we can use it in different types of problems. Let's pause here for this video, and in the next video we will be looking at some more examples with force of friction.